exact first order equations, differential equations. Now for y of 0 equals 2, we have a condition here for this equation given here. We're right again, we write this, we need this in this form here, m dx n dy, which we can see is in this form. Now, because this is not separable, so we need to write it in a kind of a ansatz sort of thing, ansatz, to get the solution. So if we write it in this form here, we're plugging in these values for this, we'll see that m equals this, n equals this. Now, since dm by dy equals d by dy of this equals 0 plus 2xy, now is equal to dw by dx equals 2xy, this equation is exact. Now first we integrate this with respect to m equals this. We are integrating this and include the unknown function h of y as a constant of integration. We get g is equal to the integral here, and we treat y as a constant, so our g becomes this here. Now we take the partial derivatives of g with respect to y this time, treating x as constant, so we get this here. Now we set d of g dg of dy equals n, and recall that n is this as from above. Now x squared y plus dh by dy equals this, where dh by dy is minus 2y. We integrate with respect to x, we integrate and keep x constant. We get this. We substitute h of y equals minus y squared into the previous equation. We get this. Now since dg equals 0, for an exact differential equation it follows that g of xy equals c, a constant. Therefore this g equals a constant, and then we apply algebra to solve for y as a function of x, which gives us this here, y as a function of x. We use the boundary conditions that we were originally given, y of 0 equals 2, to solve the constant. We plug in x equals 0, y equals 2 into the equation. Only positive roots satisfy boundary conditions, so 2 equals this, 4 equals minus c. We plug in c equals minus 4 into the solution for y using the root which satisfies the boundary condition, so our final answer is this. Now another example, given y of 4 equals 3 for this equation, we first write equation as this, as we discussed above. This is a kind of ansatz because it's not a separable equation, and we recall that this is just a notation, and this equals 0. Comparing with this, we see again m equals this, n equals this, and since our derivative of m with respect to y, we get 2y, and is not equal to of n over x, x over y equals y. This differential equation is not exact. Since 1 over n, dm by dy minus dn by dx equals 1 over xy equals 1 over x does not depend on y. We use the integrating factor, so we write this as such, and we'll get our integrating factor here. So here we multiply by mu of x equals x to make an exact equation, which we get this equation here. We compare equation with our original ansatz, to see that m2 equals this. Now n2 equals x squared y, and since the derivative of m2 over y equals 2xy equals dn over dx equals 2xy, this shows the new equation. This equation is now exact. Now we first integrate dg by dx equals m2. Now since m2 equals this, we are integrating dg by dx, this including the unknown h of y again. Now g equals the integral here. We treat y as a constant this time. We're getting this. We're taking derivatives with respect to y and keeping x constant. We're getting this. Now we set the above equation dg by dy equal to n2, and record n2 equals x squared y. Now we compare both sides of the equation to see this equals 0. We integrate this to find h equals b is constant. Since h is constant, we also get g is a constant, and set b equals to 0, and just deal with a single constant instead of 2. We set h of y equals 0, g of xy, in g of xy, since dg equals 0. And for an exact differential equation, it follows that we get g of x or y equals some constant. Therefore, we may set the previous expression for g x of y equals to a constant, which we do here. We solve for y as a function of x here, and this is our y as a function of x. We plug in the values of x equals 4, y equals 3, and only positive roots satisfy the boundary conditions given. So upon plugging these values in, we get our value for c, which is a. So our final answer, y equals all of this, which is valid for x does not equal 0. And that's exact first order differential equations. Please do like and subscribe. There's lots more to come.